Assalamu alaikum. I am Hamad Ali with another video of digital signal processing. Today my topic is fast Fourier transform FFT. FFT is an efficient algorithm for computing DFT coefficients. It reduces the computational cost to great extent. We consider a digital sequence x of n consisting of 2 raised to power m samples, where m is a positive integer. It means that the number of samples of a digital sequence x of n must be power of 2 for FFT to be applicable. If x of n doesn't have 2 raised to power m samples, we simply add zeros in order to make it power of 2. For example, if x of n is equal to 2, minus 4, 3 and 1, as you can see, the n is 4 in this case, and 4 means 2 raised to power 2. So we can apply FFT on this sequence. Similarly, if we have a sequence x of n is equal to 1, 3, 2, 1 and 2. Here the number of samples are 5, so we append it with zeros to make it a power of 2. As you can see here, we have added 3 zeros to make n is equal to 8. And n is equal to 8 means 2 raised to power 3. So it is a power of 2. Now we can apply f of t on this sequence. The formula for DFT is given as x of k is equal to summation n is equal to 0 to n minus 1 x of n e raised to power minus j 2 pi k n divided by capital N. This formula we have discussed in the previous lecture in detail, so you may be familiar with this one, where in this formula n goes to 0 to n minus 1 and k goes from 0 to n minus 1. Now if we discuss the number of additions in this case, the simple formula for this is n into n minus 1. If n is equal to 8, simply you will put n is equal to 8 in this formula and find the number of additions, that is 56. And now for the number of multiplications, that how many multiplications you require, you'll use this formula n into n. For instance, if n is equal to 8, then you'll simply put it in this formula and find 64. That is the number of multiplications required in this operation. Now let's consider an example in which a sequence x of n is equals to 2, minus 4, 3, 1, minus 2, 0, 3 and 1. N in this case will be 8 as there are 8 number of samples. First of all, we find the coefficients of DFT by using the formula that is as follows, and we have discussed this formula in detail in the previous lecture. So you may find it easier this time around, and we'll find the coefficients of DFT by putting the values in this formula. As you can see, we have found these values from x of 0 and continuing till x of 7. These are the values. As x of k is equal to summation from n is equal to 0 to n minus 1 x of n e raised to power minus j 2 pi k n divided by capital N. Now we will let w of n is equal to e raised to power minus j 2 pi by n. By substituting this value in this equation, we obtain x of k is equal to summation n is equal to 0 to n minus 1 x of n w of n power kn. Now in order to calculate the even and odd values, we have split the formula into the even portion and the odd portion. The basic formula is the same. We have just replaced n by 2r. Now by simplifying these equations, we find the even part plus the odd part into w of n raised to power k. We have simply named the even part as a and the odd part as b, just to make our calculation simpler. As the given sequence x of n is this one, we have split this given sequence into even 4-point DFT and the odd 4-point DFT. For even 4-point DFT, we have used the even values, that is 0, 2, 4 and 6. And for the odd 4-point DFT, we have used 1, 3, 5 and 7. We have simply split these into two parts, even 4-point DFT and odd 4-point DFT. After that, we have simply calculated the DFT coefficients by using its characteristic formula that we have discussed again and again. Similarly, we can divide the 2-point DFT into even and odd 2-point DFTs. Now calculating the W of n raised to power k, as W of n raised to power k is equal to E raised to power minus j 2 pi k divided by n. First of all, if we want to calculate W8 of raised to power 0, here n is equal to 8 and k is equal to 0. So by simplifying this equation, we obtain W8 raised to power 0 is equal to 1, and putting it in the formula, that is AK plus B of k into Wn raised to power k. Here k is equal to 0, so putting the values gives us 4. In the same way, we can calculate W of 8 raised to power 1, W of 8 raised to power 2. Now coming on to the number of additions, as we discussed earlier that the number of additions is equal to n into n minus 1. N was 4 and n minus 1 is equal to 3. So multiplying these gives us 12. In the next step, we have multiplied 12 by 2. This 2 means that 1 is for the even values and 1 is for the odd values. So it gives us 24. And in the next step, 24 plus 8, this 8 is the original n that was given in the provided sequence. So it gives us 32, that is less than 56 that we calculated earlier. And now coming on to the number of multiplications, the formula was simple, n into n. N was 4, so we have obtained 16. Multiplying 16 by 2, that is 1 for the odd and 1 for the even values, gives us 32. And adding the n into the 32 gives us 40, which is less than 64, which we calculated earlier. So as you can see that the computational cost is reduced greatly, and that is the purpose of FFT. Hopefully you guys have understood today's lecture.